Okay, everyone, today is the 14th of October. It is 1959, 59, 57, so we can start now. Tonight we're going to talk about the Laplace transform solutions for the, or Laplace domain solutions for the radial flow case. Again, some of this is going to seem tedious, but it's just algebra, a little bit of calculus, a little bit of transform. These are the classic solutions. And as I told you last night, you can always learn something from the classic solutions. I want to say, with the math ladies present, that sometimes when you cheat, bad things happen. And you can cheat the solution coming out of Laplace domain, but probably the solution in Laplace domain, I wouldn't play around too much with that. What I'm getting at least in the second part of the lecture tonight, whenever we try to reduce this, actually it's this part, we're going to try to take this really ugly algebraic expression and reduce it to something a little easier. What are we trying to do? Okay, so I used to have this great cartoon that I would draw, and I grew up in Louisiana, so I'm not very smart. Let's see, this doesn't work, so that's the end of that. But okay, how many of you like crabs? The things, crab trap, you guys know crab traps? No? You've seen a crab trap before. They're usually made out of wire, and you put something inside the crab trap so the crabs go in, right? And you make the door to the crab trap sort of shaped like this so they can get in, but they can't get out, okay? So I've said the Laplace transform is like getting married, and the Laplace transform is like a crab trap. You guys want to hear this? Okay, great, you will. So Laplace transform is like getting married because it's easy to get in and almost impossible to get out of the Laplace domain. So we'll talk about that. And then the other one is that, like a crab trap, it's easy to get in because you can get in through the door, but then you can't get out. So smart crabs, what do they bring along with them? They bring a bomb, okay? So they set the bomb off and it blows a hole in the trap and they get out. What does using a bomb in the Laplace domain mean? We're going to use a numerical sampling algorithm to get out of the Laplace domain. If you try to use the Moulin inversion integral to get out of the Laplace domain for this stuff, it will drive you insane. It will not work. Well, I shouldn't say it won't work, but it'll be very tedious. So what we do 99.99999% of the time is we use the Gaver-Stayfest algorithm. And I don't remember how much Alex talked to you about the Gaver-Stayfest algorithm, but Gaver deserves a Nobel Prize. He was a queuing theory person that worked for Bell Labs, the phone company, and he figured out how to sample a distribution of values in order to predict the inverse Laplace transform. It was an absolutely brilliant paper. Unfortunately, he was not much on extrapolations, so he had a great concept of this sampling function, but you would have to take an infinite number of samples in order to get the right answer, right? So that's not possible, and so he took a finite number of samples, actually a relatively small number of samples, and made a relatively crude extrapolation formula. Stayfest comes along and goes, you're a smart guy, Gaver, and all that, but why don't you try this? And he had a very simple, well, it was based on collocation polynomials, extrapolation formula, and that changed the world. So there was a direct inversion formula for Laplace transforms, and so we didn't have to use the Moulin inversion. And those of you who've done this before, the math ladies probably know this, that the Laplace transform and Laguerre quadrature are very close to each other. So they're actually algorithms defined on the Laplace transform using the Laguerre quadrature. This is one of those parts where, I know the math ladies are going to laugh a lot, but I'm going to tell you this anyway. I might have repeated trigonometry in the 10th grade. I mean, just theoretically, and well, actually I did. But so let's just not talk about that because it brings back painful memories. Actually, I didn't have to repeat it, but I didn't exactly pass. So whenever we were determining the value of pi, I noticed that the square root of 10 was kind of close to the value of pi. And I thought that I was some Egyptian 6,000 years ago with a knotted rope, and I just discovered the solution to pi. And I went up to my teacher and showed him this, and he goes, wow, that's kind of close. But, you know, still you fail. So that was not a good thing. Does anybody know the other approximation for pi, the really simple one, math ladies? 22/7, right? Okay. Of course, then there's all sorts of other things. But so I thought square root of 10 was. Okay. Enough of that. We're going to go on to your misery tonight. So tonight what we're going to do is start where we left off last night, which is take the initial and boundary conditions, and we're going to take the Laplace transform of these. And what is the Laplace transform of 0, class? 0. What's the Laplace transform of 1? 1 over u. We're going to use u for Laplace transform variable. What's the Laplace transform of 0? What's the Laplace transform of this? Well, it's the Laplace transform of that. And it could be 0. This is what I was telling you before, that I made this have an actual time function, but it could be 0. So math ladies, do you see why we're doing zeros and ones? Because this is really well suited to the Laplace transform. Okay. And then tonight we're going to derive all these. Yes, I know it's ugly. This is the so-called cylindrical source solution. This is the so-called line source solution. And this is the so-called log approximation to the line source solution. And there is actually another approximation which isn't so good. I remember a paper back in the early 80s where someone used that and got criticized from the editor, saying we have an approximation to an approximation to an approximation, but that was pretty funny. Okay, so for a bounded circular reservoir with no flow, that is, that exterior term is 0, then we have this expression. And I know that looks really, really ugly, but we'll talk about how to make it not look quite so ugly. And then the bounded circular reservoir with constant pressure at the outer boundary is kind of similar, but it is different, and it arises from the nature of the outer boundary condition. So math ladies, when you see x, k1 of x, what do you think? You don't think. Engineering students, when you see x, k1 of x, what do you think? We got lucky. If x is close to 0 or going to 0, what is x, k1 of x? It's 1. Okay, so that worked out really nice. What is x, I1 of x as you approach 0? Does anybody remember? It's 0. So, okay. So there'd be some reductions there. When we just assume that we're near 0, some nice things happen. And again, the Laplace transform variable u and time t, they are inversely proportional. So the bigger t is, the smaller u is. So these things actually get better with time, these approximations that I was talking about. Okay. So I'm going to skip over this part because I did it twice. I wasn't very smart. I told you already that. But we're going to start with this expansion for the general case of, well, this includes all cases. So the first thing we do is look at the partial differential equation. We write in its more compact form. Again, the definition of dimensionless variables, just for memory, you know, you have to remember what that is. And then our little table. And then we have all of our initial inner and outer boundary conditions here. We've already talked about these tonight, but these came directly from the lecture last night. So the first thing we do is we take the Laplace transform of the left-hand side of the partial differential equation. It is in terms of RD, not in terms of t. Everyone remembers that the Laplace transform of a derivative of something other than t is simply the derivative of the Laplace transform with respect to that. So we got off easy there. It also changes the partial derivative to an ordinary derivative. The derivative of PD with respect to TD, that term, when you take its Laplace transform, it's not trivial, but it is u, the Laplace transform parameter, multiplied by PD in the Laplace domain, minus PD of TD equals 0. Again, what is PD at TD equals 0? For all cases, it's 0. We defined it that way. So the initial condition takes care of that. and you can quote me as saying, thank God, okay? So that worked out all right. Again, everyone remembers that the Laplace transform of a derivative is simply the Laplace transform parameter multiplied by the Laplace transform variable, right? Similarly, the integral, the Laplace transform of the integral is simply 1 over u multiplied by the Laplace transform of that function. So we start with equation 13, and equation 13 seems straightforward enough, but we're going to need to do some other things to it in just a minute. We're going ahead and take the Laplace transforms of the inner and outer boundary conditions. The Laplace transform of -1 is -1 over u. The Laplace transform of 0, Eric? Mr. Desai, the Laplace transform of 0? The Laplace transform of 0? Everybody? 0. Okay. Now, in the unique case where we have a function where QD at the external boundary is a function of time, that just becomes the Laplace transform of whatever that function is, and we're not defining it here tonight. I did use a non-zero QD one time for, and I mentioned this before, to try to model water influx, which it was okay with that. All right, so the first thing we're going to do is multiply through equation 13 by RD squared. That gives us RD, dPd, drd, or sorry, d by drd, RD, dPd, drd, and that's equal to u RD squared times PD. Now we need a variable of substitution, and just like last night when we did the Boltzmann transform, this is a similar kind of a variable of substitution. We're going to go ahead and define z is equal to the square root of u RD, which of course tells you that RD squared is then going to be equal to z squared divided by u. But in our case, we're going to have z squared is equal to u multiplied by RD squared. And it'll all work out in just a minute. So the first thing we do is take the chain rule, apply it here, apply it here. We already know that z is equal to the square root of u multiplied by RD. So what's the derivative of that class? Square root of u. No surprise there. And then, of course, we have another term here. Everything's going to be fine. So we substitute the definition of RD here, and we substitute the definition of z, and we have z divided by u multiplied by, square root of u multiplied by square root of u, z divided by square root of u multiplied by square root of u, and then we have z squared PD on that side. And so what that ends up being is a form that is z d by dz, z dpd dz, z squared PD. We're going ahead and expand it. That gives us z squared times the second derivative, z times the first derivative, z squared times the function itself. We go to the Handbook of Mathematical Functions, which I provided a copy for you in the references, and technically this is a government document, so it's seen as being public domain, so I can do that. And then we have z squared multiplied by the second derivative of w with respect to z squared, z first derivative of w with respect to z, and then z squared plus v squared multiplied by w. So what is v for our case, class? It's 0, okay? So the general form of the solution, or sorry, the general solution, pardon me, for equation 26, which is the modified Bessel's differential equation, is w is equal to a I of v of z, b k of v of z. So what is v for us? It is 0. So our solution is PD of z is equal to a multiplied by I0 of z, b k0 of z. It's that simple. We're done. There's your general solution. So that's the nice thing about Laplace transforms, is that things work out. Now, math ladies, what do we have to do? We have to figure out what A and B are. And how do we do that? We have an inner boundary condition and an outer boundary condition. So we need how many equations and how many unknowns, class? We've got 2 unknowns, we need 2 equations. So we're going to go ahead and take the derivative of the general solution. We may need it, we may not, depending on which case we're solving. Okay. So now we'll go ahead and write out the full solution. It is the general solution, I should mention, that PD of RD of U, A, I0, square root of U, RD, B, K0, square root of U, RD. That's our general solution. And again, our goal now is to determine A, determine B, so we have the particular solutions. So we have to derive the derivatives of equation 29. When we do that, we're going to need to use the chain rule again. I'm probably going to stay with equation 28 actually, but whatever we do, we're going to need the derivative of PD with respect to RD, and then that gives us the chain rule dz drd dp dz, and then we work out the algebra again, looking back at how we define z, and that gives us dpd drd is going to be square root of u dpd dz, and then we're going to have to do it again. But at any rate, we continue out and we expand these terms. We take the derivative of each. Now we need to know what is the derivative of I0, pardon me. Well, we got really lucky, class, because these Bessel functions have reflection relationships, which are that the derivative of I0 is I1. The derivative of K0 is minus K1. So life's pretty cool, right? So we continue with our derivation. We're still in terms of z, no problem. We're going to go ahead and substitute the definition of z into here. And then finally, we'll write it in this form because we're going to need an RD, DPD, DRD term. And when we do that, we have A square root of URD, I1 square root of URD, minus B square root of URD, K1 square root of URD. So the two important equations so far are 29 and 37. So summarizing everything so far, we have 29, we have 37, we have the inner boundary condition, and then we have the 4 possible outer boundary conditions. Okay, so let's take a quick rest break and ask ourselves, how do we solve these? Well, always one of the cases is going to be what? What's one of the conditions? The inner boundary condition. It's a derivative. So every time we're going to need to use, oh, sorry, I can't read without my glasses. We're going to need to use equation 14. So every single time we're going to have to solve equation 37 for the condition given by equation 14. Is everybody all right with that? No problem. So that will always be one of our equations. Now, the other ones, we have kind of a weird situation here for the infinite acting case, because here PD as RD approaches infinity is going to be equal to 0. So that means we're going to use equation 29. Now, what's the behavior of K0? K0 comes down from infinity. I'm going from x equals 0 to x equals infinity. It comes down this way and goes like that. So what's the long-term behavior at infinity of K0? It's going to approach 0. On the other hand, what does I0 do? I0 starts at 0 and goes up, not exactly exponentially, but similar to that. So what's its behavior at infinity? So what's going to happen to that term? It's going to get to go bye-bye. Okay. So we're going to have to figure out, that's what I was talking about before, is there's a boundedness constraint, and that's not going to work. Okay. So the first case we'll solve is the infinite acting case. So it'll be the outer boundary will be A, the infinite acting outer boundary. And when we do that, we of course start by looking at the inner boundary condition, which I've already said. So this equation 38 is always going to be something that we have to use. So we're always going to have to use equation 38 for the inner boundary condition. But for the outer boundary condition, like I just said, we're going to have to look at the limit as RD approaches infinity. And by definition, what's going to happen to A? A's got to be 0. It can't be anything else. Because as this group goes to infinity, this term goes to infinity, and A must be 0. There's nothing else that can cancel it out. Excuse me. So by definition, A is going to be 0. Everybody can already see over here, and I misspoke, sorry, I0 starts at 1. I1 starts at 0. My apologies. But nice hand sketch there too. Thank you. So now we come down and we solve for B from equation 38. In doing that, we find that B is equal to 1 over U, 1 over square root of U, K1 square root of U. Now, we'll talk about this in a minute, the behavior of square root of U, K1 square root of U. What is it going to look like? Well, as U goes to 0, this is going to go to 1. So again, A0 is that. And here's our final answer for the so-called cylindrical source case. Now, as I mentioned, if we go back to the text and we look at the behavior of K1 near 0, the behavior of K1 near 0 is 1 over x. And if, of course, we multiply that by x, then it's going to be approximately equal to 1 as we approach 0. So square root of u, K1, square root of u, or whatever it may be, as square root of u approaches 0, that's going to go to 1. So our final sort of intermediate result is here, and we often call this the line source solution. Now this looks really easy. Unfortunately, there is not a direct table lookup for this anywhere except Carslaw and Jaeger, which is a textbook that actually you were supposed to buy for this course, but I'm sure nobody did. So what we're going to do is, well, when we get to that, we'll cheat. But we're going to take and we're going to expand K0. K0 actually has a logarithmic term, and it's right here. If you look at the expansion, it's also multiplied by I0. And I0 at 0 is what, class? It's 1. Okay, so as we're close to 0, that term will go away. And of course, anything that's 0 squared or 0 to the 4th or whatever it might be, those terms are all going to die off as well. And so we're finally going to be left with K0 really being just approximately equal to this. And that's on the next page. But I0 is approximately equal to 1 as x approaches 0. So our nearly final form is here, and then we make our substitution and we do a little bit of cleanup. And of course I made it this way because this is all a constant, and you can it's a constant divided by u, so whenever you take the inverse Laplace transform of this, it'll just be 1/2 natural log 4 over e to the gamma 1 over r d squared. But whenever you take the inverse Laplace transform of this term, it's going to be a little bit different. What's an unusual thing about a logarithm and the Laplace transform? Does anybody remember? I think it's the only function that is the same in the Laplace and the real domain. So the Laplace transform of a logarithm is a logarithm, just FYI. We'll come to that in the next part of this derivation. Okay, is everybody ready for case 2? And we will stop after case 2. I'm not going to completely make your brain explode. Okay, everybody ready? So we have equation 38, right, which is our derivative condition. We've already solved equation 38 for the inner boundary condition. And what do we need to do now? We need to solve it for the outer boundary condition. So going back, sorry, I was misreferencing. It's equation 37. So before we solved equation 37 for the inner boundary condition, and that was equation 38. Now we're going to solve equation 37 for the outer boundary condition of b, which is equal to 0. So in one case, at rd equals 1, it's equal to minus 1 over u. At the other case, at rd equals rde, it's equal to 0. So this is fairly straightforward. I know it doesn't look like it. It looks horrible. But first thing we do is we take equation 37 and we combine it with the outer boundary condition, pardon me. And this is simply equal to that. So I did a little bit of algebraic manipulation here and just said, okay, we'll solve that for the b parameter, and it's equal to that. Now, somewhere along the line here, okay, I recall the inner boundary condition, equation 38. Algebraically, there's probably an easier way to do this, but I'm really lazy. I mean, we need to solve equation 49 and equation 38 simultaneously. So what I did is I just went on ahead and solved equation 49 for b, and I'm going to substitute equation 50 into equation 38. And when I do that, I'm going to have this expression, and of course then I solve it for a, and a is going to be this god-awful term here. And then, of course, we know that the definition of b is equal to here, and so we just substitute a into that expression, and that gives us b. So when we collect all the terms, we have this. So I know I'm going through this really fast, but you guys are smarter than I am. This all makes sense. It's just algebra. We had to have the outer boundary condition and the inner boundary condition are both derivative conditions. So we set up the equations. We have two equations, two unknowns, and we solve it algebraically for this. Any issues? No? Okay. So now, is this not the ugliest thing you've ever seen? So how do we make things disappear? We cheat. So the behavior near 0 of square root of u, k1 square root of u is 1. The behavior near 0 of square root of u, I1 square root of u is 0. Okay? So first of all, we look at this behavior, and it is going to be 1. We already know this, but that's okay. And then what is going to happen with I? Okay, so I1 is approximately equal to this. Going ahead and multiply it through by that. We take x is approaching 0, and so x, I1 of x is approximately 0 as x approaches 0. Same thing with square root of u, I1 square root of u, no problem. So this is the final form. Now, is this easier to solve, boys and girls? Well, is equation 54 easier to solve than 53? Yeah, it is. Remember, the Laplace transform and the inverse Laplace transform are linear operators, so we can do this term by term. Okay? The first term we already know, because the first term is it's actually, this term. It's the infinite acting term. So isn't that cool that this solution tells us this is the infinite acting term and this is the finite acting term. Again, this is a bounded circular reservoir. So this is where the behavior is logarithmic, and this is the add-on term. Okay. Are you going to find this in any book? The inverse Laplace transform to that? No. No. I want to give you a little historical footnote, okay? Everybody, again, take a deep breath. When's the first time this solution showed up in the literature? What year? 47? What article? Well, the full solution did. When, actually, let me ask this question in a minute. Okay, can everybody hold their breath until we get to that? All right. So the next thing that you don't want to do, the constant pressure outer boundary is easy. The non-constant value that we talked about before of allowing this thing to be a function, that one, the algebra is a bit more hairy, but it still works out that you can do this. Okay, so you can still obtain a solution with this the external boundary term, and of course the external boundary term really becomes an add-on here, and of course if it's 0 then it just goes away. But you can't really reduce this very much, just FYI. Okay, so are there any questions about how we got to equation 54? Okay, I'm going to stop the video.